think that perhaps a good compromise would be that you purchase the cables, because what's going to make it easier for you is if you don't have very heavy cables to haul around, even just transporting it. And of course the cost of a cable is a lot less if it's shorter than it's longer, right? So that way you could just rent the actual data collection unit, own the cable yourself, and that would be your largest expense.
So, from what I understood, as far as the cable has to be manufactured specifically to our needs and what the spacing would be.
Not necessarily. So when you work in a field, there's the rate that you can work at, right? How fast you can get this data. It depends a bit on the weight of the system. If you're working with a system that's meant to go half a kilometer or more, but you only need to use 100 meters, you can have a lot of extra cable to deal with, right? In that sense is what I'm suggesting. That might be actually a good idea to go with a custom-made cable that's very short, 200 meters, something like that, 150 meters, kind of designed for your purpose. But to test it out, I think, going with what we have off the shelf is the best thing, because it's easy. You can just grab it, go. You can go deeper or shallower. It's just you end up working with, think of 6 meters of cable and you're only going 2 meters. So you end up with 4 meters of cable that's just laying there, you're carrying around for no reason.
Oh, I got you. Okay.
We can always make a large system that can go deep, do the same measurements as a small system, but you have all this extra cable that you're having to deal with and roll out and roll up.
Okay.
And when things are heavy, field crews, people who work in the field, they tend to not be as careful with things when they're heavier, because it's just a lot harder to move things around. You end up tossing it, and the cables are very, scientific equipment. It's rugged to be outside, but you never want to pull on it, and people try to take shortcuts when it's heavy. And to be successful, you need you need equipment that will actually be working.
Right.
Right. Okay. So here, let's see if I can get the where's the remote or someone. Okay. I'll just Here we go. All right. So this is our Earth Imager software. And we put a lot of work into it. Just to give you an idea, we released it 624 times.
Wow.
Yeah, so that means that we've fixed bugs or added features to it. And we started basically, I guess it was about 12 years ago. So it's really full featured. But if I can go in here in our demo directory, you can download this demo for 30 days and just play with it and do stuff. Here, I've got the various types of cases that people have submitted. So some of these are not relevant to what you guys do,
Mm-hmm.
but
how about that iron ore one?
you do iron ore one, okay.
Unless you have something more.
No, that's fine, but it's not relevant to what you're doing.
Right. Okay.
But yeah, we can do anything. I was thinking I'd do this one.
Sure.
Pyramid. Okay, so here's some data collected. These data points represent that current and the voltage measurement and the coordinates, right? And then, so before we had this type of software, we would just kind of plot a pseudo section of apparent resistivity. It's not the real resistivity. It's kind of like a guesstimate, because we didn't have computers that could handle this type of processing until the mid-90s, right? And also this one has terrain on it, because it's a pyramid. So we'll make sure that we actually use that. So it's very simple. I read in the data. We just choose surface settings here. There's a lot of settings that you can change. See, and most people are not going to understand what that is. But if you just choose that and then hit that inversion button, it starts calculating the response. Okay, so by selecting surface, I set all the defaults for surface so that you have a good starting point.
So what you're looking, what we're looking at here, so the green, orange, yellow, blue, what are we looking at? What are those?
Yeah. Let me explain what this
Okay.
is. Okay, so first of all, if we see that top section right there, that is your measured apparent resistivity. So the measured data is the voltage divided by the current, right? That's basically how there's a mathematical equation you can derive apparent resistivity. Apparent resistivity is kind of like a weighted average based on modeling different kind of geologic situations. It's an older way that people used this technique. This technique was founded not by us, by the Schlumberger brothers. You know, now there's a huge company called Schlumberger, and they're in the oil business, right? And what Conrad Schlumberger was doing was that he's doing wireline logging of electrical resistivity for hydrocarbon deposits, coal and things like that in Normandy, in France. And that was like 1915, 1918, something like that. And so this method has been used since then. It wasn't until the late 80s we designed this equipment, basically, put a microcontroller in it, automated the whole system. So we didn't invent the method or the mathematics behind it. We just brought it into the 21st century. And so this is what they would work from before. So you can see that this model or this data right here doesn't look anything like this, right? Because it's not taking into consideration that this is actually it's a buried pyramid. So what these guys were looking for were entrances, like areas like this, where they were hoping to find an entrance to the pyramid.
So the colors is the resistivity or the conductivity of
resistivity. So here's very resistive. This is all in resistivity. It's on log scale. So red means very resistive. Think like air, dry, not a lot of pores. Here, think moist, conductive, like clays, silts. So depending on this range, and of course this goes from near zero. Zero would be a superconductor. That doesn't naturally occur, but copper is very, very conductive, right? And then on the high end here, it would be, in this situation, I'm not exactly sure, it's probably voids, things like that. That appears everywhere in the earth. You hear about sinkholes and things. It's more prevalent than you think. And of course you can see there's some kind of layering here. Looks like there's runoff from water coming down here. This kind of conductive. Blue does not mean water, by the way. It means more conductive.
right.
But it makes sense that if you're in the rainforest and this rains all the time, it's going to be drier up here and more resistive down here. I mean, more conductive down there. Okay, in any case, so what I wanted to say is that, so this is the data that we actually measure, right? So it's based on the current we transmit and the voltage that we measure. Okay, remember that each one of these points, there's actually, even though that spatially we plot them like this, there's no spatial relationship. Okay, so this software, what it does, it takes a computer model. If I roll this back to the very initial model, it gives you homogeneous. Homogeneous means one property, right? Same material, 86 ohm meter. Ohm meter is the unit. And 86 happens to be the average of this data that we collected, because we have to start somewhere, right?
Mm-hmm.
So it starts with this, and the forward models some data. Now you can see the effect of just the topography created these two features, or these three features, that conductive area, this resistive area. Why? Because, it's not flat, right? And I'm giving it the same property here. So now, what the computer does is that it creates this model, and then it calculates depending on the physics of the problem, right? It calculates what the delta V, the voltage divided by the current would be, and then plots it here. And it looks at this and it realizes, it's not exactly the same. So it tries to improve on this model to make this look more and more like this, right? And so you see now that was the first iteration. The next one changes the model here, and the synthetic data, or the calculator repair resistivity, is now matching this more and more and more, right? So we try to collect the data as clean as possible so that our computer model will as accurately predict this data. It's a very strange way of thinking about interpretation, because like in ground penetrating radar, you actually see what you see in the data. You don't need to process it, you're just looking at it, right? But for us, all we have is a bunch of electric fields and distortions that electric field that are basically saved as the voltages that we read. And then from all those distortions, we have to figure out a model of the Earth that will fit all that data. And to complicate things further, mathematically, there's an infinite amount of these models that will satisfy the same data. So we use statistics, and that's what the software does. It takes a statistical ruler called a norm, and we try to look at it statistically, how will we fit this data to the actual data, but not so close that we incorporate noise. Remember we talked about Nyquist. So we assume there's a certain amount of noise inherent in our measurements, because you're placing the probes, you're not getting exactly, as careful as you are, you might not be able to get it closer than a centimeter, or the line, varies a little bit, it's not exactly in line, and there's electrical noise, and there are all these different processes causing noise. So we try to model data really close, but not to the actual solution. That way we get a very generalized solution that has less detail. Because we know that we have, by the Nyquist sampling, we know that we can't measure, or we can't distinguish any details smaller than half the spacing. So we don't try to look for anything smaller.
Okay.
Okay. So it's called inversion. That's what the modeling technique is called. It's the same type of technique you have in MRIs and things like that. But our starting model is that.
Mm-hmm.
It'd be nice if we knew where the ear and the nose were and things like that. Sorry. Okay. So let's look at another case.
So, looking at this one, the 150 mark on the x-axis, that's the distance of the or the length of the cable. Is that what?
Okay, so this is the distance of. In this case, I have meters chosen, but I can show it as in feet or the electrode number. So if we look at number of electrodes, looks like it's 51, 52, 53, 54 electrodes in this particular.
And the
case.
spacing between them?
The spacing between them is 3 meters.
So 1.5 meter is what you would be able to see as far as resolution goes.
Yes, but you remember this is a pyramid.
Right.
This is an archaeological thing. So this is rather large. You see that the depth here from, let's see here, that's elevations 272 down to about 247,
Mm-hmm.
35 meters.
It's huge.
Yeah, it's it's like typical pyramid.
Right.
I don't know what a typical pyramid is. This was done by, I think it was a university who went down there.
So what did they do? Just run this the cable up on the pyramid and then scan it?
They just went straight over.
Okay.
But I think there's better ways. So this was a while back they did this.
Okay.
You could do it in even better ways, like you do 3D, but that wasn't really accessible to everybody. Our technology is quite new. If you think in the last 24 years, and the last 15 or so has been like, 3D, but you remember 3D is more expensive because it doesn't involve just doing one line like this, it involves doing several. So
I think I'm pretty sure we're going to be interested in 3D only.
yeah, I think there's going to be 2 steps. When you collect the data, you're probably going to do it in 2D. So you're going to be able to look at the data right away like this. So as soon as you download the data, you're just going to bring it over here. This one's a dam instead, and you just push this button right here. Okay. Now there's a couple more steps, and I'll show you as far as reducing noise, if there's noise in this dam. This happens to be a fracture underneath the dam, and we did a demonstration for them, and they ended up buying 2 systems because they knew about this fracture where the water was leaking under the dam, and they told us to line up over it. Of course, they didn't tell us where the fracture was, but of course this makes it easier to find, because you see that this resistive layer is broken up here,
Right.
but it becomes more conductive.
Mm-hmm.
This being like, you can see here, right down there it says 330.5 ohm meter. And this come over here, you see it's like 100 ohm meters, about 99.5. So this is actually used one part of the data, so there's actually another one over here. So we compared some different arrays, just a little bit more advanced. But this was our old generation of equipment. One channel took a lot longer to collect. That's why you don't see a lot of data points. So in any case, it gives the people who are looking for fractures and water an idea of what you would see. It's a case history. But the idea is that you read in the data, you know, you pick, let's see what else we have. Beaver holes, I don't remember this one. See, it's a lot more data. Let's see if there's, I think there might be some terrain to this one too. Not sure. Nope. Okay, so we just do that, invert the data. Okay, you can see where the beavers have buried down, and they have a chamber where they live in. This application obviously has nothing to do with amber or mineral exploration. In this case, it's somebody who's trying to understand where these beavers are, because they maybe have to be relocated, or they have to design some way to recover them and relocate them. You know, so some clients have used this stuff to look at transpiration of plants. This is the process of plants sucking water out of the ground, and in the process of photosynthesis, they take carbon dioxide in the atmosphere and carbon monoxide, and through photosynthesis they create, in water, they evaporate out water and create energy, right? Sugars for the plant to grow on. But in the process they have to suck water up, and it basically evaporates, transpirates it's called. And this is important for people who are trying to cap some kind of waste product, like in landfills. You don't want water coming in and infiltrating into there and washing out all this nasty stuff. So they plant, usually it's like eucalyptus, because this has a very high rate of transpiration, and so that they can keep the cap dry. And in other cases, so like in Australia, they had millions of acres where they removed all the eucalyptus. And what happened then, because there was none of these plants actually taking the water and evaporating out, they introduced a saltwater layer that killed all the vegetation. Because people didn't understand what they were, you know, by removing the eucalyptus, they didn't realize the damage they would cause to their farmlands, so they were no longer farmable. So there are scientists who look at that and be able to see the fluid being taken out of the ground. We have clients who do that. We have clients who use this equipment to look for tunnels for escaping prisoners, you know. It's just imaging. Another client, this was part of USGS, there was a guy who did a study on tree sap. So they just put nails into a tree, and then they would measure the seasonal variations of the fluid moving up and down the tree like this, because they're living organisms and the sap is like their blood. And throughout the seasons, the sap moves up and down, picking up water, and it's gonna, you know, when it's during the spring, you get leaves again. So then it takes these minerals, and they create like little hydrocarbon chains of sugar, starches, for the whole plant to live off of. But it does this through photosynthesis, so all that water's gonna come up, and then, you know, really interesting stuff.
Right.
But, you know, applications are different.
Could you actually show me that iron ore?
Yeah, of course. Well, of course. So in this case, we're doing another thing called IP. And you know, there is a possibility that amber would exhibit this property. So now you know about us creating electric fields, but there's also another, so analogous to electric circuits, so resistivity would be like a resistor. Then you have another component that describes the ability of material to absorb charge and hold it for some time, like a capacitor. Meaning that when we put the electricity on here, we can actually pump electricity in there and charge up a body. Some materials, very few materials, actually will take charge and hold it for some time. you know, as soon as you turn off our electric field, now you have a new electric field of this body that actually charged up. Kind of, you know, battery is a storage device for electricity, so is a capacitor.
Mm-hmm.
So if you think of that, like there's, in this case it's sulfides. Sulfides are what we look for in mineral deposits. Like that's how mineralization, like metals, are actually transported into a deposit, is through.
How would you test something like that? The charge?
We just tested on the material to see what it is. You know, how it works.
So you could try and feed a charge through it and see if it or how much of it is left after you turn off. But how would you image it as far as knowing?
Yeah. So then, like, let's say now you turn off the electric field. Before we were making measurements when the electric field was on, right? Because that describes how the current is flowing through the ground. Well, when you turn it off, now there's no electric field from us.
Mm-hmm.
So we just pumped a lot of electricity in the ground, a lot of energy in there,
Mm-hmm.
and that can be stored by certain things like clay, graphite, and sulfides, and some hydrocarbons, as far as like when we're looking for pollution, usually like there's a thing called L-NAPA, which is like gasolines that are less dense than water will float on top. And then there's also D-NAPA, which are dense non-aqueous phase liquids, which are like very poisonous for people. They come from like chemical spills and things like that. And so those type of things can give off this kind of effect. So basically, directly after you turn off I'll show you what actually I'm talking about here. So we inject so if we think of this as an axis, this is in time, and this is voltage. So this is of our transmitter. Okay, so we turn on some voltage, some current flows, and during this period we actually measure the voltage at these other locations, right? And then we turn it off. And when we turn it off abruptly, there's some time for the electronics to dissipate this energy, and you know, it doesn't exactly go you know, instantaneously off. There's some milliseconds there. But if you have IP, that would mean that like somewhere in the ground you have some kind of thing that's been charged up with charges like this, right?
Mm-hmm.
And because when we apply this voltage, we polarize the ground like plus minus, right? So then you end up with these kind of interfaces everywhere. So, actually, I'm sorry, let's just look at this body here. So you kind of polarize these, you kind of make them go opposite directions inside each material in there, whether it's amber or anything else. And then what you do is when you turn this off, well, then these charges want to migrate back to come to a zero voltage, right? Because you just used energy, potential energy, to move them apart.
Mm-hmm.
You're physically moving them, that's what's happening. So when they migrate back, that voltage drops off like this at some rate. So it may be less, very quick, or it may be very long. So we measure this, the amount of discharge, okay? Then using the same mathematical work, we can actually find out, you know, where this was and to what degree this target actually discharged. I've never seen or heard that amber stores charge. We can always test it. That's one of the nice things about this is it's very easy to find minerals in the ground because they are associated with something called sulfides. Sulfides are chemicals associated with hydrothermal transfer processes. So at the ocean spreading centers. So this is the ocean, right? Here you have magma coming up here, kind of in the plates are coming apart. Well, you have this kind of thing where there's a water cycle that goes down like this, you know, many kilometers
Mm-hmm.
deep, right? And it picks up minerals down here. It can be gold, silver, copper, molybdenum, all the minerals, right? And they're attached to things called sulfides. And then the hot water is denser, so it comes up here, and when it comes closer to the surface, it gets cooler, right? And so when, it happens to be in chemistry, when you have minerals in a solution and you cool it, it's like super saturated down here. When you cool it, they fall out of the solution and crystallize. And you get these, you know, huge deposits of minerals. And of course, as these things spread over hundreds of millions of years, they end up underneath the continental shelf. And as they they're piled on top of miles and miles, and this crust moves. It's a big geologic process, but basically they end up somewhere on a continent, and we try to find these deposits because they're worth billions of dollars. Whether you're looking for gold, copper, the world needs those kind of resources.
Right.
But yeah, so IP is it could be useful for you guys. I'm not sure, but
Do you have the capability here to test?
yeah, we
But-
can test it.
But you said you've never heard of it holding charge or anything of that nature.
Well, that's the thing. It's like I have only the things that I know can hold charge, like some clays can, if it's disseminated, like in particles, and graphite, and sulfides, some hydrocarbons. So, there's a lot of different materials out there, possible materials, and they don't exhibit this. Well, they do exhibit it, but it's the relaxation of that electric field is so fast that it's almost like not readable.
Okay.
So this is like the ability of something that acts like a capacitor. Think of this here, like a battery, right? Separated charges, and then
See how long it lasts.
yeah, of course a battery is like long term, like it has an internal resistance, and unless you give it a circuit back, it's not going to flow, right? But a capacitor is almost instantaneously discharged, basically on the rate of milliseconds or seconds, and a battery can go hours.
So something or this type of application would work to look for, say, coltan or that type of mineral.
Like coal?
Coltan, I think it's called coltan.
Oh, they're associated with the mineral or the
Battery. No, it's a different application.
Okay.
Yeah, it's coltan. It's mainly mined in Africa. It's used for microchips, batteries, things like that.
Lithium maybe, or cobalt, or
No, not cobalt. They call it coltan.
coltan. Well, that may be the mineral. That may be the mineral name, and in that mineral they'll refine it into some kind of
Oh, I see. Okay.
yeah, like batteries are typically like lithium or nickel, cadmium, NiCad batteries.
Okay.
Nickel metal hydride batteries. Yeah, there's a lot of. I'm sure there's there's probably designing some type of cathode, anode in there that it requires many different minerals. Yeah, but everything we use in the world needs minerals. Gold is needed to be put on contacts. Copper is needed for running copper wire, or aluminum is needed, and also creating PCBs for electronics. Aluminum is needed for airplanes. Just to name a few. Steel is needed to make cars.
Right.
So, and rebar and concrete. And as a matter of fact, we don't only just look for that, we also look for the sand and aggregate used for the material in concrete. That's also like a mineral in that sense. And then of course water is another very important.
Right.
We actually kind of think of water as a mineral because it's a resource that we humans need. And as the Earth is being populated more, it's becoming more and more apparent that there's not enough water. For example, here in Texas is a good example of that.
Yes.
Farmers in West Texas don't have enough water, and the people don't have it. The farmers down in Southwest Texas need it for the rice farms. So moving water around, trying to find new things. Of course, California's the big thing right now, the drought that they have. So people are drilling their own wells, trying to get fresh water. Yeah. So what I want to show you with this here is that it's extremely easy to process this kind of data, because I just, I read in the data.
So before you leave this one here,
Yeah, I was just going to read
Okay.
the same one again, yeah. Go ahead.
So looking at this again, the x-axis that's the length of the cable,
Yeah, it's in
and each
distance.
square dot is going to be the electrode.
In this case, it's just electrode number, but let's go to meters. Yeah.
Okay.
So this is actually very analogous to what you're going to do. 162 meters.
Okay.
Or,
And every of those, one of those square dots is going to be the electrode that's put in the ground.
right, that's just an electrode, yeah, so you
Okay.
can see here, just at an even spacing.
Okay. And
So you would lay out these along, the sides, maybe 1 meter, 1.5 meters, 2 meters, 3 meters. You lay out the cable, attach them with the spring, like that. So you imagine it's just how long it takes you to do that operation times 56 or 112 electrodes.
you did say that it's important to have them on a, say if we chose a 1.5 meters for a distance apart, then it'd be important to keep that consistent as close as possible. Otherwise, the reading wouldn't be exactly.
No, I mean, there's no, we do it because it's easy that way, and because it gives us a uniform resolution across the section. But you could literally put electrodes anywhere. I don't think you'd want to though, because you would have an uneven spacing. You'd have like 1 meter spacing here, maybe 2 there, so it would be like in the area where you have 2 meter, you only got a 1 meter resolution, and in the area where you have 1 meter spacing, you only have a 1/2 meter resolution.
So it'd be difficult to map it, and
Yeah, it doesn't make sense to do that, because you'd end up adding kind of artifacts due to the spacing. So the spacing becomes a filter. So to make this complex situation less complex, just keep an even spacing. It's easy to lay out, less mistakes.
okay.
But let's say if there's a big rock in your way and you can't put an electrode there, well, you can't put an electrode. A lot of our clients are working like in suburban areas where you have a driveway or a street. You can't put an electrode in it. Then you just have a missing electrode, and you're right.
How does the system read that when you have a missing electrode?
Well, for example, I could come here and actually just delete an electrode. So let's see here. Edit electrodes. I can take one of these. So number 30 would be over here somewhere. I just take this one and remove it. And there it's gone. Now I can actually look at my data here. You can see all black. It's all gone.
So the black was where the electricity was traveling through the ground, and you could read the resistivity.
No, the
on it?
black is missing data.
Oh, I see.
Yeah, it's missing data.
Wow.
So if I click on any one of these, then you can see. Okay, so in this case, so we have these things called arrays. Arrays are different combinations how we're going to measure. So in this case, you see that the transmitter is only one, but you need 2, right? You can't send electricity around with 1 electrode. You got to have a return somewhere.
Right.
So we're just not graphing it, but it's actually far, far away from this area that we're mapping. It's called a pole-dipole array rather than, 2 dipoles, dipole-dipole. So we have different names like pole-dipole, pole-pole, dipole-dipole, Schlumberger, Wenner, gradient. So these are all different combinations on how we take measurements. And one of the nice things about the pole dipole is that it has a very strong signal, but it lacks some resolution. That's the drawback.
Which of those applications is the most going to be able to give you the most resolution?